Good morning, students. Today we will talk about an important theorem, which is known as intermediate value theorem. And through this theorem, we will get to know this today that why we usually say that a continuous function doesn't have any gap or any break, but this statement is a vague, but we will clear it. Continuous functions where and what type of sets and what type of domain should a continuous function have, so that we can say that continuous function doesn't have any gap. But prior to that, we require some results. Only one result that we have stated it as a lemma. This is our requirement. This will be used in the proof of the intermediate value theorem. And this lemma in itself is an interesting result. It states that suppose you have a continuous function defined on an interval, and see we are taking this semi-open interval, and if at a certain point x naught in this interval the value of the function f x naught is positive, then there exists a positive number epsilon and a point x1 in this semi-open interval ab such that x1 is bigger than x naught and the value of the function uh, is greater than epsilon for all points in this closed interval x naught to x1. So we have this kind of situation. Let us try to understand it with graph. What this theorem is saying, suppose you have this interval a and b, and at certain point, of course that point x naught is different from b. If at this point the function takes a positive value, of course that means it is lying on above the x-axis. Suppose this is f of x naught, and so therefore graph is somewhere, this part of the graph is somewhere here. Okay. Okay, so then it says that you will get a point x1 which is greater than x naught, such that for every value between x naught and x1, for every value between x naught and x1 on this closed interval, the function will have a positive value. That means you cannot expect in case of continuous functions to change the sign of values immediately, because if at a certain point at x naught the function takes positive sign, means it's positive value, positive sign, then in a neighborhood in nearby points of this x naught, function will have the same sign, function value will remain positive. So this is more restricted version, but within proof I will tell not only the interval from x naught to x1, we will get a part of the interval towards the left of x naught as well. We will get a much larger interval which will include x naught as its center, such that on this whole part of that interval function will have a positive value. So let's go to this proof of this. Okay, so we have this, that there exists certain epsilon lower bound for this, positive lower bound for this function. So this choice of positive lower bound is quite obvious for us. It is the fx naught upon 2. And since you see this, that fx naught is positive, fx naught being positive, its half will also be positive. Therefore, let us take this epsilon to be this fx naught upon 2. And now let us look at this thing also. Since x naught, we have chosen x naught to be less than b, that simply implies that b minus x naught is positive. If it is positive, its half is also positive, and let that half be denoted by delta naught, this number. Now it is clear this thing that you have this interval a to b, semi-open interval, and x naught is you are choosing x naught somewhere here. Then b minus x naught, you look at this this thing b minus x naught. I can say this thing that b minus x naught upon 2 upon 2. So I can write it to be less than b upon 2. It is less than or equal to b upon 2, and this is less than b. Yeah, that's okay. That means delta naught is less than b. That's the one thing that you can say. But at the same time, if not this way, if let me remove this, we can do certain other things to verify this. But now let us take certain point in this interval. Uh, that means uh, x you are taking in this interval, closed interval a x naught plus delta naught. That means x naught x is less than x naught plus delta naught. But look at delta naught ka value. You have the value of delta naught x naught plus you will have b upon 2 minus x naught upon 2. So what will be left to you? Let me change the color to make it significant. Then moving on to here, x naught minus x naught half will be x naught half. It is b upon 2 minus plus x naught half. And see, x naught is what? X naught is less than b. So it is b upon 2 plus b upon 2. It is b. So that this gives us that if x is less than x naught plus delta, then x is less than b also. That means x naught plus delta naught has to be less than b. Only then that's the reason x is less than b. So this computation tells us that whenever you choose a point in this closed interval a semi-closed interval or semi-open interval a to x naught plus delta, then that point will by computation fall in the original interval, which is the domain of our function. Okay, this computation is now let us apply the definition of continuity, because your function is given to be continuous at the point x naught, and according to the continuity it says that for any epsilon greater than 0, but for here we will take our epsilon that we have selected at the beginning. For this choice of epsilon, I will be able to find a certain delta such that whenever the distance of the point from x naught is less than delta, here it is not 0, it is delta, then the f of x minus f of x naught has to be less than epsilon. But here I have taken a particular value of delta. And how we can do this thing? Because if I have taken delta to be less than delta naught, we can do this choice. Why we can do? Because if by definition your delta comes out to be greater than or equal to delta naught, then this inequality star, let me denote it as star, this inequality star holds for those x where x minus x naught is less than delta. But this inequality, this x minus x naught absolute value less than delta, means this is some interval center with x naught. One endpoint will be x naught plus delta, another endpoint will be x naught minus delta. And if this inequality star holds for every point, if it holds for every point in this interval, so it can hold for this inequality shall hold true for any subinterval of this interval. So if we take any other smaller interval, it will also hold. And we can take this smaller interval, and this choice of smaller interval is possible. Therefore, depending to make this delta less than delta naught, we will select, we can make this delta further smaller, or we can take smaller delta of this delta if it is greater than delta naught, because doing this will not affect our this inequality star. This is why, that's why I have chosen this delta to be less than delta naught. Okay, now now what we have to do, from this equation star is this f of x minus f of x naught, its absolute value is less than epsilon. Epsilon is what? Epsilon is f of x naught upon 2. Now, you're referring to this mm, uh, fundamental theorem of absolute values. This implies you will have a minus f of x naught upon 2 is less than f of x minus f of x naught, and this is less than f of x naught upon 2. Now, I will use the additive property of numbers, and that will not adding throughout some number, this inequality will not change the order of this inequality. And what I am going to add, I am going to add this number throughout the inequality. Then what you are left with, you are left with f of x naught minus f of x naught half less than f of x, and this is less than f of x naught half plus f of x naught. Let me call this inequality alpha. So now what you have, the at this equation alpha, the left part of this inequality is what is the conclusion of our theorem, but with certain modification, because what is what is here in this box now, uh, this fx naught minus fx naught half is fx naught upon half. This whole thing is left to us now epsilon, and it is less than f of x, and this is true for all. This is true for all x in this interval x naught minus delta, x naught plus delta. So this is what I had already told, because epsilon is positive, so fx is positive on this whole interval whose center is x naught. But we require its precise form, and for that what we can choose any x1 greater than x naught. And then if this inequality holds on this entire interval from x naught minus delta to x naught plus delta, then it will this inequality will hold over any closed subinterval of this interval, and in particular it will hold on this subinterval x naught to x1 also. And this is the conclusion, because it will hold there. Okay. So now coming to the proof of intermediate value theorem and its statement, but there might be using this convention, what it means for a number to lie between two numbers. So the number y naught is said to lie between two numbers c and d if one of the following holds: either c less than y naught less than d, or d less than y naught less than c. This this is the word we will use here to lie between numbers. And this theorem 2 is the intermediate value theorem. This is the intermediate value theorem. Okay. So suppose a less than b. To make a less than b means this will make our interval, closed interval a b, a non-degenerate interval. And suppose you have a continuous function on this non-degenerate interval, and if y naught is some number which lies between the value f of a and f of b. That's the simple. So look at this. You have this. Then it says that there exists a point x naught in the open interval ab such that value of x naught, a value of f at x naught is y naught. So let us try to see what this theorem is actually telling us. We can say also this, that any value between two values of a function is also value of a function. We can also note this in this way, that any value between two values of a function, two values of a function is also a value of function. We can also remember this in this way: value of function, value of the same function, not a different function. And on graph, what it says that suppose you have interval a b, And suppose this is somewhere here, it is f of a, and suppose it is f of b here. Then the on the graph, the coordinate corresponding to this value will be a, f of a, and corresponding to b, it will be somewhere something b, f of b. So theorem says that any value y naught is also value of the function. That means this y naught also corresponds to some coordinate here. It also corresponds to here some x naught, y naught. This is, and this y naught is for this f of x naught. And in this way, that means this any value, whatever value to you take between f of b and f of a, and in this way, you will be able to see the graph of the function from this coordinate a, f of a to b, f of a will be a connected line, will be a connected curve. There will not be any gap because every point from f of a to f of b will correspond to a coordinate on the graph of a function. And that's why we say then this thing that graph of a continuous function doesn't have any breaks or any jumps, but graph of a continuous function on intervals only. अगर आपका फंक्शन इंटरवल पे नहीं है तो देन पॉसिबल है कि योर फंक्शन है इज कंटिन्यूअस but still it has gap. For example, look at this function. If I define f of x as 0, if 0 less than x less than equal to 1, and I define it as 1 if 2 less than equal to x less than equal to 3. Now you look at the domain of this function is the interval closed interval 0 1 union the closed interval 2 3. So it is not an interval, it is a union of two disjoint intervals, and this is some set, and this function is continuous there. You can check it, it's a continuous there, but it has gaps. You can see, you plot its graph. This graph is not a connected like the graph I have shown here. The only feature of intermediate value theorem here is that your domain of the function is not an interval. If the domain of the function is an interval, it is a connected line segment, then your graph will have no jump or no break. Okay, so this is the essence of this theorem, but let's move on to its proof. So f of a and f of b are different values. So one of them is bigger and other is smaller. So we suppose here that f of a is smaller than f of b, and since y naught lies between them, so then y naught must satisfy this inequality. F of a should be less than y naught and less than f of b. And now we are defining a set E. On set E, what we are doing, we are taking those values of point interval, those points from the interval AB whose function value is less than y naught. And now see, by your assumption, A must be in E because the value of A is less than y naught. That means E is a non-empty set, and also look at this, E is a subset of the interval AB, and this interval AB is bounded. And we know that a subset of a bounded set is a bounded set, therefore E itself is a bounded set, is bounded set. So E is a non-empty bounded set, therefore completeness axiom can be applied here. We will apply completeness axiom on it, the existence of its supremum, and therefore it will have a supremum and it will have a finite real number as its supremum, and let that supremum be denoted by x naught. So x naught henceforth is a supremum of this set E, which is a non-empty set. And let me tell, this x naught is the point which we will show to have function value equals to y naught. This is what we have to show. And we will also show that this x naught is actually lying in the interval AB. That means it is not equal to A and not equal to B also. But we have to refer to another property because we have involved supremum, and look at this. And this is called the approximation property of the supremum. And approximation property, how does it come? It says that you can choose a sequence in E such that that sequence converges with supremum x naught. How it is possible? How you choose this sequence? Because look at this thing. X naught is supremum. So every number, every point in the set E is less than or equal to the X naught. But if I subtract something from this supremum, it that by definition it will not be a supremum, because supremum is the least upper bound, and so it is not a upper bound. It is not even upper bound. It's not even upper bound. If it is not a upper bound of E, then some element of E must be bigger than this number, and let that number be xn. And but xn has to be less than or equal to x naught, because x naught is a supremum. So this can you can do for every n, हर n के लिए you can select this तरह है. So in that way you choose a sequence in E, and xn will be in E, and this sequence will converge to x naught. Why it will converge to x naught? Now you just take n to infinity. You just take n to infinity. If you take n to infinity, this part will converge to x naught. This is already x naught, and then your this squeeze theorem implies that xn also converges to x naught. So this way you apply this approximation property of supremum, that supremum of a set is always a limit of a sum sequence in the set. Okay, so this is justified why we are choosing this sequence here, because this is possible to do. And now we will work this with this sequence, because we have to use continuity. But also now, since this sequence xn is in E, and E is a subset of interval AB. This is a closed interval, so the sequence is in the closed interval AB. If this is in the closed interval AB, that means A is less than or equal to xn less than or equal to B. And therefore, again, uh, if you can refer to comparison theorem, so by comparison theorem of sequences, xn is converging, therefore its limit has to be less than or equal to x naught less than or equal to B. So that simply implies that this limit is in closed interval AB. So this is actually a general result that sequences in a closed interval, convergent sequences in a closed interval, contain their limits in the closed interval. Their limits cannot go out of the interval. So this x naught has to be part of this closed interval. Okay, why it is beneficial for us here to have this x naught in the closed interval? Because now your function will be defined on this x naught. So this point is a defined value now. Now look at this. Each x naught, each xn is in E. If each xn is in E, by definition of E, the value of function at xn is less than y naught. And this implies, by again by comparison theorem, limit of this sequence f of xn will be less than or equal to y naught. But your function is continuous. So continuity, xn converges to x naught. So sequential continuity says that f of xn will converge to f of x naught. So this imply continuity, by continuity f of x naught is less than or equal to y naught. Okay, so you have reached at a point where you have shown that f of x naught is less than or equal to y naught, but you want to show that f of x naught is equal to y naught. Okay, so f of x naught is less than or equal to y naught. You want to show that f of x naught is equal to y naught. Suppose this is not the case. If this is not the case, then the only possibility left to you is that f of x naught is less than y naught. Okay, suppose this is true, that f of x naught is less than y naught. Then what happens? Then we consider the function, some function, let me denote it by g of x as y naught minus f of x. Suppose this is the new function, which is here y naught minus f of x. So it is a function. It is the difference of two functions. Y naught is constant, fx is a constant function. F is continuous, y naught constant being continuous. So this is the difference of two continuous functions. It is a continuous function. And this is a continuous function on this interval AB. And what happens at point x naught? Because at point x naught, g x naught is y naught minus f at x naught. Because your assumption is that f of x naught is less than y naught, therefore this has to be positive. So that means this is a continuous function which has a positive value at a point x naught on this semi-open interval. And now here we appeal to the lemma. Our lemma says that if it has a positive value at a point, then it doesn't have one positive value at only one point. It will have positive point at lot of points towards the left side of x naught. So in particular, there will be a point x1 and epsilon x naught will be x1 will be greater than x naught because this has to be to the right side of not left to the right side of x naught such that the function will have a positive value. Indeed, that value will be greater than epsilon, and epsilon itself is a positive. So now y naught minus f of x1 is greater than 0. And so this means that fx1 is less than y naught. If fx1 is less than y naught, the definition of E implies that x1 has to be part of E. But at the same time, x1 you have taken to be greater than x naught, and x naught is what? X naught is supremum of E. So what you are happening? What is happening here? X1 is an element of set E, but at the same time, this element is strictly greater than the supremum of the set. This is not possible because every element in a set is less than or equal to its supremum. How is it possible that there is an element in a set which is greater than its supremum? So it is a contradiction. If it is a contradiction, therefore, an assumption that f of x naught is strictly less than y naught fails. Therefore, the only thing that is left to us is that y naught has to be equal to fx now, and this completes our proof. But since we have in the proof we have claimed this x naught to be lying in the open interval ab, and this will follow from the fact that we have assumed that f of a is less than y naught is less than f of b. So if x naught is equal to a without loss of generality, that will imply that f of x naught, which is y naught, will be equal to f of a, which is not possible. Therefore, x naught cannot be a, and similarly, x naught cannot be b. Okay, so this completes the proof of the intermediate value theorem. So this is one of the important measure, and you see the proof of this theorem depends on completeness axiom. Completeness axiom is, as I said, the founding pillar of this real analysis. If it is not there, nothing is there. Okay, let's try to apply this intermediate value theorem to some of our exercises. So we have f and g are continuous functions on AB such that value of f at A is less than value of g at A, and f at B is greater than GB. So you have the opposite relation. f की वैल्यू A पे छोटी है g की वैल्यू से, और B पे भी g की वैल्यू से बड़ी है. So let's try to see this through graph. So you have the function A and you have the function B. So f of A is smaller. Let this be f of A, and g of A is greater than. So let us g of A will be greater than. And now in case of the values of the functions f and g at B, f of B is bigger than. So let us take f of B here, and g of B is smaller. So f and g both are continuous functions, and intermediate value theorem says that their graphs will not have any gap, and f of b का end point होगा यहाँ पे. So it will be graph like this. This will be the graph of f. And now let us look at the graph of g. Graph of g will start from somewhere here, and its endpoint has to be somewhere here. This will be the endpoint of this graph of g, b, g of b, and its beginning point will be here. So this graph has to start somewhere, because it has to go from this point a g of a to this point, and it has to be connected. So it has if you draw, and you have to draw it without lifting the pen, because intermediate value theorem said that the graph of g will not have any gap. But whatever way you do, it will have to cross the graph of f. At certain point, the graph of f has to be crossed by this function. And suppose this is the point where this is the point where and what is this point? At this point, this is C point. At this point, the two values of the functions becomes equal. This is a graphically, but if you want to prove it directly, what you can do, you can define a function h of x is equal to f of x minus g of x. Then you see the value of h at a. It is a continuous function on interval a b. Value of h on a is f of a minus g of a. It is positive because f of a, no, it is negative. H of a is negative. Okay, yeah, it is f of a is less than g of a, and h of b. H of b is what? H of b is f of b. So it is positive. So now you can see this thing that mm, uh, 0, 0 is some value. Let me write it in this way. Uh, H of a is less than 0 and 0 is less than h of b. So now this 0 will work as a y naught in the intermediate value theorem, because h is a continuous function at the interval and y naught is a value between h of a and h of b. Therefore, intermediate value theorem says that there is a point h of c will be 0, and this h of c will be 0 means f of c minus g of c is 0 means f of c will be equal to g of c. Okay, this is the case. So as an application of this exercise, we have this next exercise, which is an important exercise. It says that if you have a self map from the interval to itself, if you have a function which is defined on set E and its range is also in the set E, then you call that such a function as a self map. So here it is a self map, and it's a continuous self map on the closed interval. It says that if it is continuous, then f has a fixed point. Fixed point means there is a point in interval AB such that f of c is equal to c. Fixed point होने का मतलब है कि उस पॉइंट की इमेज वही पॉइंट खुद से है, वो फिक्स हो रहा है, वो चेंज नहीं हो रहा है फंक्शन अप्लाई करके. ओके, तो सॉल्यूशन के लिए व्हाट यू हैव टू डू, you have to consider above one function, because exercise 2 involves two functions. Here first let us look at f of a. F of a, because f of a has to sit in the interval ab, so f of a has to be greater than a, and similarly f of b cannot be greater than, because this is the function का range interval ab में है, so it has to be less than b. So you consider another function I of x, identity function. Then you consider h of x as uh, f of x minus I of x, or simply you can consider f of x minus x. Then you see that this, if you apply this exercise, previous first exercise, then by first exercise one function is f, another function is I, you will be able to find there is a point where h of x is equal to 0, or f of c is equal to I of c. Then you will be able to find that f of c is equal to I of c. I of c is c identity function, because you have this comparison now, because mm, you can say this way. You will have this I a को मैं लिख सकता हूँ I of a, and b को I can write I of b. Or yeah, h पे you directly applied intermediate theorem on h, because h of a is what? H of a and h of b, one is taking the positive value, h of a is taking the positive value, because f of a, h of a is getting the positive value, and this is taking the negative value. So now 0 is lying between h of a and h of b. Therefore intermediate value theorem says that 0 is a value of function. So h of c will be 0. H of c will be 0 means this will be f of c will be I of c. And this is this that will be the fixed point of this function. And this is a very standard result. This is a very important result that self maps always have a fixed point. You can see graphically what it means. Graphically, it will means I will not go into that. Graphically, it means that the self maps on the open closed interval will always intersect the diagonal of the square that is formed by this cross product of the interval AB cross AB. Okay, I will stop here.